Hey guys, it's Professor Dave. Let's talk electrorefining.
He knows a lot about science stuff. Professor Dave explains.
Electrorefining is a process in which materials, usually metals, are purified by means of an electrolytic cell, which indicates that the process is non-spontaneous and requires a power source to proceed. Let's say we want to obtain pure copper from an impure copper sample. This means that the sample could be mixed with different metals, higher or lower in oxidation potential, and is found at the anode. For the rest of the cell, the cathode must be a pure copper sample, and the solution must be a salt containing copper 2+ ions. The goal here is essentially to plate the pure copper with more pure copper obtained from the impure copper electrode. As seen here, the power source causes the impure copper electrode to lose electrons, undergoing oxidation and becoming copper 2+ ions in solution. The lost electrons travel through the wire to the pure copper electrode. Here, the electrons cause the copper 2+ ions to gain electrons, causing them to form pure copper, which plates on the pure copper cathode. This process is repeatable with many other different types of metals. As we learned in last week's video, this is accomplished with redox reactions. To tell you more about how and why these reactions work, let me send you over to my good friend Sal from Khan Academy, and he'll show you exactly why this happens.
Alright, let's say we have a battery here, 0.34 volt battery, and we're trying to get pure copper through electrorefining. So in our anode here, we have mostly copper, but we also have some impurities. We have some zinc and we have some gold, let's say. So what happens here if we run 0.3 volt current through this battery? So for higher oxidation potential metals than copper, the oxidation potential of zinc, for example, it's way higher than that of copper. As you can see over here, the oxidation potential of zinc is 0.76 volts compared to that of copper, which is 0.34 volts. This means that zinc is more likely to donate all of its electrons than copper. Now, this means that if a current is applied, all the zinc in the anode is going to lose all their electrons before copper, since its electrons are less attracted to the atom. So these sort of all fall out. All the zinc sort of fall into the solution as zinc 2+, and we got a bunch of those in here, which means in our battery we have no more. Now only after all the zinc is oxidized will the copper begin oxidizing when we run 0.34 volts. Over here we can see that the oxidation potential is 0.34 volts. The reaction is as follows over here, according to the completely illegible table of standard potentials. Now there are much more copper 2 cations in solution than there are of Zn2 cations. So now all this copper here, all of it falls into the solution as Zn2+. Oh no, as copper. It was copper. Great. Splendid. Now what about for things that have even lower oxidation potentials than copper? Now, if we run 0.34 volts into this battery, anything that's higher on this chart, anything here will not be oxidized because it simply does not have enough voltage. So, for example, gold, which has an even lower oxidation potential than copper. So this is what remains after all that oxidation has happened. We've got a bunch of copper 2+ ions and zinc 2+ ions in solution, and we've also got gold over here in our anode because it never was oxidized because our battery here did not have enough voltage to oxidize it. That is the acceleration in which the gold will fall into the solution, and it's going to form this little thing called anode sludge. Because there's nothing holding it together anymore. All the copper is gone, which is like most of the anode. So yeah, let's look at the cathode now. So remember that there was already a fat amount of copper 2+ cations in the solution. In the solution, there would be 3 possible species now: copper 2+, zinc 2+, and gold. As electrons flow from the anode to the cathode, keep in mind, copper 2+, which has 0.34 volts, is more likely to be reduced than zinc 2+ at -0.76 volts. And now, since there is so much copper ions at all times in the solution, the zinc here never really will be reduced. So now we have all these copper 2+ ions electrons are flowing here, creating attraction between copper 2 plus and electrons. And this will cause a huge lump of copper solid to form. So that is simply the equation here for oxidation. So copper 2 plus 2 electrons yields us solid and pure copper. And that is how we form a pure copper through electrorefining.
Thanks for joining the show, Sal. If you have any further questions, feel free to contact me at Professor.
Oxidation, reduction, higher potential, lower potential. By now I know you're wondering, what do I need to know this for? What is this used for? How can this help me? Well, today we're going to be talking about the importance of electrorefining. As you may have learned from Professor Dave, electrorefining is one of a collection of electrochemical processes which is primarily concerned with the extractions of metals from their ores and or subsequent refining of the metals to a higher purity. Basically, the main advantage of electrorefining processes compared to others, such as electroplating and electrowinning, are that they are designed to handle wide variation in the quality of the base scrap and conversely can provide a particularly high purity of end product material. Now, highly pure metals are extremely important for everyday needs. Some of the different applications for which high purity metals are required include research, development, sanitary and or sensitive laboratory work, and the productions of advanced technologies. For example, some are magnetic while others are thermoelectric and or semiconducting. These can include metals like aluminum, brass, bronze, carbon steel, copper, and tungsten, and among others. These highly pure metals are used in the creations of fluorescent lighting, plasma screens, LEDs. So basically, without electrorefining, you can say goodbye to all of your beloved technology, all of your beloved foods, processed foods, and much more. So goodbye to everything. Anyways, that's all for today. To summarize, today we talked about the process of electrorefining, and a big shout out to my best friend, Professor Dave and Sal from Khan Academy. If you guys missed anything, please make sure to check out the timestamps listed right here or here, and I'll see you next time.
If you have any further God, dude. Thanks for joining the show.